Hello, we're going to talk now about how to represent a binary tree in a different format as an array. So you have to understand a rule, which we'll talk about in a couple slides. Compared to the linked representation, the insert and fetch algorithms are simple. It's also order log n. And the density is better than the linked approach when the tree is balanced. So basically, here's an example of a tree off to the left, and to the right, an array with the nodes, the keys filled in to the array. So the root is G, and its left child is D and its right child is I. Let's look at D, for example. The left child of D is B and the right child of D is F. So 2 times 1 is 2 plus 1 is 3, and that is the index of the left child, B. 2 times 1 plus 2 is 4, and that's the index of the right child, F. So that continues on down for every index, for every key in the array. The children are 2i plus 1, 2i plus 2. So sometimes you may have a tree that is not left balanced, and in that case you should put in null values to make it left balanced. And so, for example, for 60, 2 times 2 is 4, plus 1 is 5. That's the left node of 60, and we put the value null in there. For 29, both of the children are null. But in order to make it left balanced, we say both of them, 7 and index 8, are both null. So here's the rule, and you have to just memorize this rule: 2i plus 1, 2i plus 2. So a couple of rules, a couple of processes that you go through, steps. The first step is put the root in the 0 node, and from then on you can use the 2i plus 1, 2i plus 2 rule to locate the index of the array. So index I, if index is 0, 50 goes there. 0, 2 times 0 plus 1 is 1. 40 goes there. 2 times 0 plus 2 is 2. So 60 is the right child, and it goes in index 2, and so forth down the line. Here are some examples of various trees stored as array-based trees using the 2i plus 1, 2i plus 2 rule. Now, when you get down to the arrays that are skewed, you'll see a lot of nulls, and that's because we want this array to be left balanced. So the left child of B is null, the left child of A is null, and the left child of A. Both of them are also null. So the insert algorithm is fairly simple. We check to see whether we want to go into the left or the right subtree, and then we, instead of using the pointers, the left child and the right child pointers, we use the rule 2i plus 1 to go left and 2i plus 2 to go right. And then when we find the right space, we insert the element in the ith node. Similarly, the fetch algorithm uses the 2i plus 1, 2i plus 2 rule, again, the same way. So this Again, in a balanced tree, the execution is order log n. In a highly skewed tree, it becomes order n. The density is a little better than a linked list based, because we don't have to worry about the links, the left child and right child. The delete operation can be fairly slow. For example, if we wanted to delete the root node, we'd have to either copy everything up or redo the whole tree, the whole array. We could mark the node that we wanted to delete and just ignore it in the fetch and delete algorithms. So we have a library class called TreeMap. It's an implementation of a red-black tree. We don't have to worry about how it's implemented, but it is fairly fast. And it's generic, so you put in the element that you want to go in the tree. Here's the relative values. Notice that the array-based tree, 2i plus 1, 2i plus 2 rule, in the delete and update have a pretty poor complexity, whereas all the rest is good. So let's talk about the tree lab. Here's your instructions. You download the document, do the lab, either using PowerPoint or print out the PowerPoint and do paper and pencil version, and then submit the completed PowerPoint typed in or a screenshot of your paper version. Submit that in Blackboard in the normal places. The lab is due a week after the Thursday after spring break on March 26th. So here's the lab. First of all, you're given this tree. It's a binary tree. It also happens to be a binary search tree, but it doesn't need to be. We don't mention that. And you should list out the in-order traversal, the pre-order traversal, and the post-order traversal. Now, it so happens that since it's a binary search tree, the in-order traversal prints the nodes out in numeric order, not so much with the pre-order and post-order traversal. So what's the height? Well, you can count how many levels there are. There are a certain number of levels, and what nodes are on level 2. Now, this question, part D, part 2, depends on whether you're more attuned to Carano or McAllister. Carano starts at 0, is the root node. Carano starts at 1 as the root level, and McAllister starts at 0. So if you're a McAllister fan, there are 4 nodes, these nodes on level 2. And if you're a Carano fan, then there are only 2 nodes on level 2. Either way, it'll be acceptable when we're grading it. Now here's a binary expression tree, and we do the in-order traversal again, and we do the post-order traversal. Now when we do the in-order traversal especially, we need to remember to put parentheses around each subtree. So 7 modulus 2 gets a parentheses around it. 48 minus the quantity 7 modulus 2 gets a parentheses around it, and so forth. The post-order traversal doesn't need those parentheses, because it automatically puts the post-order traversal in the right order to be evaluated. Now part C and D deal with whether this is integer division or float division. Now, if you've done the in-order traversal correctly and you've put parentheses around each subtree, you'll see what the value evaluates to using integer division. And you'll need to reevaluate it using float division. Now, by the way, the in-order traversal and the post-order traversal give the same answer. So it's not a question of which one do I use. I've occasionally been asked on Part C, well, which one do I use, Part A or Part B? It doesn't matter. I would suggest using Part A because that's the algebraic form. Okay, so the third page of the tree lab, I've already filled in the value you should use for the dummy value, null. But Part B is what you need to fill out. So given a tree to the right, use the 2i plus 1, 2i plus 2 rule to fill in the array to the left. Remembering that 14 is the root, so it goes in position 0, and after that, the sub trees go in using the 2i plus 1, 2i plus 2 rule. So we take an existing tree and put it in an array. Page 4 does exactly the opposite. It takes an existing array, and the requirement is to place it into a tree. So that's it for the tree lab. Download the tree lab from Blackboard and turn it in on March 25th, Thursday. I think it's March 25th, the Thursday after we come back from spring break.